I always watching this workshop series. That's a source of a bunch of really interesting, relevant ideas, but it's always hard to go to KDT because it's not quite my conference. But this time, well, since I was invited, there was no excuse not to go. So it's an exciting workshop. I hope it's continue. So I'm going to talk about what we're doing in our lab and trying to look at the problem of personalized learning from my take. And the difference, I guess, because I was working with it for about 30 years. And over this time, personalized learning has been going through a bunch of different changes, from expert-driven personalized learning to data-driven. And I try to look at that more or less symmetrically. So what I want to talk about is how we transition from expert-driven to data-driven personalized learning and what exactly we're doing in our lab. So first of all, what is adaptive personalized learning? Personalized is typically used now, adaptive was used before, but technically it's about the same. What we want to do, we have to teach or support students differently because we know who they are. So we try to model various features of individual students or group of students, and we try to do better than we can do without knowing that. So adaptive testing, for example, can try to present you the easiest, the most informative test, so the whole testing process become faster. In adaptive education, you can get multiple goals because there are quite many types of that. So here just a very short list. The oldest type of personalization was adaptive sequencing, which get you like a rabbit out of the hat every time, the best educational thing to do. Good example, good page to read, good animation, maybe good problems to solve. It's called sequencing. Adaptive navigation support generalized that try to provide guidance to the student, not necessarily by telling this is what you have to do, but providing interface which helps students to find the right thing to do, using essentially the same information but in a more user-centered way. Mastery learning and classic intelligent tutoring system is another kind of adaptation when everyone is going through the same sequence of problems, but we monitor how well you're doing. And if your mastery reach specific designated level, you're done, you're moving to the next topic. Very simple but useful personalization. Also, there are lots of personalizations not based on knowledge. All these three examples is the most popular knowledge-based personalization because we trace what you know, and it's also the most successful so far. By far most successful than any other educational personalization, which could be also based on goal, styles. But for a change, we can show a style adaptive hypermedia, where we take into account your learning style. Don't ask me what is that, but there are things like that. And try to do different for different learning styles. So here are a few examples of all of this technology. This is problem sequencing in our old LMR system, where every time we try to give you the best small education problem. It was an ITS, a web-based ITS to teach programming language list. So this is mastery learning in classic Carnegie Mellon algebra tutor. Here we get the skillometer, which is tracing the level of every individual skill. And as long as it's reached the specific level, we can move to the next problem. This is adaptive navigation support and adaptive hypermedia. So here, by providing different colors of bullets, we try to indicate whether a specific textbook page is ready for you to be learned, or maybe yet too complicated. And if it's too complicated, you ask for help. If it's red, if it's green, you can go. But also it can be white, which means, yeah, well, you have never read it, but there's no new information. You learned all of this stuff before from other places. And also you can actually see why this is so, because you can see what kind of background concepts and outcome concepts on the page. So you get the guidance, which help you to decide. And this is style adaptive hypermedia, which provide different navigation, different type of navigation support for different kind of students. And that's, of course, should be looking all Greek for you because it is. So this is a specific interface created for field-dependent learners. So now, how we can actually make that personalization work? Well, personalization is not a free lunch. Everything costs, and here we need knowledge. So now the question is, where we get the knowledge? And that's exactly the critical question which define the differences between several types of personalization. So in knowledge-based personalization, for example, what we typically need, we need to get domain model, a set of concepts or rules of the domain. We need to get a mapping between educational content, a problem example, and domain concepts up to the every learning step in ITS. So we need to get some student modeling rules, how we can get from observations what student is doing to the state of their knowledge. We need to get personalization rules, how giving their state of the knowledge, what we should do next after that. So do a lot of stuff. Learning style-based personalization is kind of easier, but it's still a lot of knowledge. we need to figure out what is the learning style of that guy. Typically, it's a long questionnaire, like 40 questions. After the student answers the 30 question, he said, well, he's visual analytic. Ooh. And after that, the students expect miracles from the system because 40 questions, the system knows everything. Miracles typically don't come. And then we need to get a mapping. Okay, so he's visual analytics. What does it mean? What we should do for that visual analytic guy? Should we recommend him to watch a movie instead of reading a textbook? For example. By the way, this is not working, just like an example. So this is the way with domain modeling typically done in ITS and adaptive hypermedia. We built a very complex domain network of concepts and rules over which we actually model the student as an overlay model, and every educational piece of content some kind of connected to a bunch of concepts. So this problem, when you do it, you will actually practice this and that concepts, and this example. And the problem of doing, and you succeed, well, then this means this concepts are kind of mastered a bit more. So again, this is one of example of knowledge. Whoa, where do we get this knowledge? As I said, there is no free lunch, we need to get them. So typically, classic ITS, adaptive hypermedia, almost all of the personalized learning are expert-driven. That means almost all of the knowledge are provided by domain experts, pedagogical experts, system developers. So the knowledge provided by experts, good, high quality, but hard to extract, expensive, hard to scale. And worse, they may be actually biased, because you believe into something, you put it in your expert knowledge, and actually may not work right, because you may be mistaken. So that's why we try to switch to data-driven personalized learning, where this knowledge is extracted from data. And that's actually good potential for scalability, especially with getting a lot of educational data. Also provides us a bit more objective, more reliable way of doing that, which can avoid biases introduced by experts. So what kind of data-driven personalization? So what kind of critical issues that we can get? For example, one of the dimensions which I want to classify our work, so this is a very primitive classification, 2 dimensions. One classification dimension is where we get the knowledge. So where we can extract that? Well, the knowledge are not getting from nowhere, we need to extract them from wisdom encapsulated in data. Whose wisdom is that? One source is wisdom of instructors. Instructors create courses, they create whole educational programs for us, which courses to take, in which order, for example, if at the higher level. They provide specific content, they write textbooks, but there are some limits to that, right? There's also wisdom of the learners, and then the learners are going through problems they solve, successfully or fail, they look at the example, then after that they solve problem or not, and all of that knowledge can be actually measured by the success. We have multiple textbooks, but students who use these textbooks learn much better. I guess it's kind of better quality of knowledge in this textbook. So the outcome is what really makes data-driven personalization hopefully more reliable. Now, the other question is how this knowledge could be used, and there are generally 2 main ways. First of all, the knowledge may empower the humans. We may present them to the humans in a kind of clear way, typically visually, and then I can call it visual learning analytics. On the other hand, this knowledge can be used to empower the algorithms, the decision making, and that's the majority of people in this field are working on. So, although there are some really nice examples when we empower the humans, Irene has been presenting a very nice example where knowledge extracted from data can empower instructors in analyzing student solutions. So, visual learning analytics is still kind of a bit less presented in the personalized learning, especially data-driven personalized learning. The idea here is to present to some human, student, instructor, some information which might help learning better. It might support students in managing their learning process, choosing what next things to do, and then in the next course, it's self-regulated learning. We also support instructors or even decision maker. If the chancellor looks at the data, presented in the right way, they say, ooh. And that's exactly why the university management really likes learning analytics, right? Because they give them the data and they feel that they understand what's happening. Sometimes they do. So the other approach is educational data mining, where we actually try to get labels and just labels. Because educational data mining is more fuzzy, but the majority of work, they try to mine the data to improve the algorithms. While visual learning analytics, the majority of work try to use the data to empower human decision making. But of course, there is a kind of overlap. So educational data mining will try to extract the data to improve some algorithms, which is a critical for personalization. Better domain modeling, it's a part. Better student modeling, maybe better adaptation, right? So, and that's the way I'd like to present the work in our lab. I wanted to make sure that I presented everything a little bit of everything. This is overview of the work. There is a URL, so I don't want to tell everything because slides are going to be available. I'll try to show you the work, a little bit of the work in all dimensions. So students, teachers, whose wisdom is, better interfaces, better decision making. I'll show you just 3 examples, and actually I'm going to run out of time anyway. I'll try social navigation, open social learning modeling, where wisdom of students and used to present better interface to the students. I'll show problem-solving genome, when we also mine the wisdom of the students, but now try to do better decision-making. And also show you mining prerequisites from outcome and from textbook, which in fact can contribute to both. It can help, this is the wisdom of experts encapsulated in textbooks, but we can do better interfaces and better decision-making at the same time. So I killed 4 horses with 3 bodies. Oh, chickens? Well, no, let's don't kill anyone. So the first idea, how we can use social wisdom to help students through the interfaces. So one of the approaches we use is social navigation support. It's a very old idea in the field of HCI. Basically, we use the data for previous people to guide future people in multiple different ways. So how we can do it? There are many ways. One of our earlier approaches was a system where we try to do adaptive electronic textbook by showing students what other students are reading in the very same week. And since we recommend several different textbooks to the class, it's actually quite hard to find what exactly you would like to read. But it turns out, as a whole, students are really doing a very good job in finding the right places. And we look at their traffic, their navigation support, and their annotation behavior to find sections which are most important to read and most valuable. We have several evaluations which shows that's actually quite right. So density of blue color here indicates how much students are either reading or annotating specific sections. And the density of human color shows how you're doing that. So for example, if there's a dark blue box with a white background, looks like everybody is reading that section, but you're not. Maybe something is wrong with you. Maybe actually not. Maybe everyone else is wrong. So we're now doing a next round of that. The trouble with traffic-based navigation support is unreliability. It's not always when you come to the page, you come for a reason. We found out there are a lot of honeypots or tar pits where it looks like a very nice title in the textbook. Everyone wants to go there, and they're just garbage, right? But however, you need to be very careful figuring out when it's really good or when it's not good. So we're trying to also play with the reliable traces, and we call it open social student modeling. Open social student modeling, trying to look at how you perform and contrast it how everybody else performs in a structured form. Well, I think showing it's probably better than explaining it several times. This is one of our recent versions. It's an open source system called Master Grids. So here we get a contrast between the student performance in the programming course. Every row is a topic. So here is variables, data types, constants, loops, and stuff like that. And the density of the green color represents your level of knowledge achieved in different topics. Now you can also look at the knowledge which achieved by the whole class or your referential group, like top 10 in the class. You can choose which group you're using. So now it's a class average. And there is a contrast row which tells you who is doing better. If it's more green, then you're ahead of the class. If it's blue, you're behind the class. You have to see the whole class, how it's working along that. So it's a kind of a big picture, but you can drill it down because in every class there are multiple types of learning content. For example, in our Java programming course, there are examples, there are animations, and there are semantic problems. So you can contrast yourself and your performance with every type of the problem. You actually can see that sometimes on some type of problems you're always running ahead of the average of the class, but on other cases you're always behind. So you may pay more attention to that. This is a very rude navigation support because we don't take any account of student exact performance, like concept by concept. We only allocate their performance to class weeks, which we treat as topics, which is a very rude level of integration. Surprisingly, it works really like a champ. So we're actually very surprised to see that the quality of navigation support provided by social approach is matching to the quality of providing knowledge-based guidance. Students get to the right problem at the right time. So it is about the same quality and is significantly better than the situation where knowledge navigation support is not provided. But what is always remarkable in these attempts, the students work considerably more on non-mandatory problems and examples. All of these problems and examples are non-mandatory. They provide it for the students just to explore, to increase their knowledge. And guess what? If we don't give them points for that, they just don't do it. Right? There are a lot of nice technology. Turns out they will provide the social navigation support, showing how they are doing, how class is doing. The amount of their work is increasing 3 times. And their retention in class also increasing 3 times. 3 times, right? And this is indication when if you have 10% increase and it's significant, everyone applauds and you report it as a big conference. So 3 times is a very large margin. We can read the papers about that. Why engagement is important? Well, of course it's important. You know about MOOCs, we're in trouble, everyone drops out. But not only, there's a lot of things which teachers now able to provide. It's excellent content, which is still not quite a part of the course. You use it because it helps you to learn. And the main trouble with educational technology right now, if you try it in the lab, it works. When you try it in the class, nobody uses it. Right? Why? Because it's not for grade. It turns out grade is not really important. Students need some kind of acknowledgement. So with social incorporation and acknowledgement they're learning, they can do quite a lot. All right, switching. Right? Now let's try to mine student knowledge and do something which we can extract from data for guiding them. And again, I try to get an example of what is kind of different from what many other people are doing. We're doing a lot of other kind of stuff like matrix factorization, like everybody else, but this is something which is slightly different. We're trying to learn the sequence of student problem to do some kind of data-driven style-adapted personalization. So learning styles have been criticized because a lot of work on the learning styles turns out to be junk. But yet, we know that individual differences exist. So what is wrong? Maybe the existing questionnaires, they have been created all, by the way, 30, 40 years ago, before computers. Maybe they're just not catching the right learning styles, which are essential for modern computer-based education. But if students are different, we should be able to see it from the data. So how we can look at the data to figure out what is the difference? And we use a bunch of different approaches to mine student data, and we found one which was called Learning Genome, which is working like really nice. I want to show a very simple example of that when we're dealing with parameterized Java exercises. This is the exercise that students need to predict the value of the variable or final result. And what is good about that, when they're wrong, they can try again with the different parameters. So you can try the same exercise once, twice, 5 times. There's always a different one. We want to figure out how to guide the students. Should you try it again, the same exercise, or should you actually move on to the next exercise? So it turns out that we can use the sequence mining. So we're trying to figure out how long students thought about an exercise and whether they're successful or not. And we use a complex, I guess I need to speed it up, but slides will be shared, don't worry. The paper is available. So we're using an approach called Learning Genome, where we're trying to extract reliable repeating sequences, and we create student vector representation, which we call genome, which represent the frequency of each sequences. Turns out that genome is exceptionally reliable. It's like you can describe who the author is by looking at the text. There are multiple parts of the text, how you use an article, which word you choose, and we can say, oh, this is Theodore Dreiser, and this is Ernest Hemingway. It's very hard to mock, right? Same as like artists. So we can figure who you are by looking at as you solve the problems. Now what we can do with that? If it's really reliable, it really represents you. But we still need to figure out how to use that to do the guidance. So what we did, we clustered people by their genome, and we tried to get them down to just 2 clusters. And it turns out that we can divide the people by 2 very distinct groups. One of them we call kind of confirmers. They kind of overdo on this problem, solving the same problem again and again. Especially they solve it again when it's very easy to solve. Maybe they're very happy because they can say, correct, right? And then they actually need to move on, but they don't. On the other hand, we have another, we call not confirmers or clearers. They solve the problem once, they fail, and this is it. But in fact, would they try once again and once again, they will do it. So this is kind of really distinct profiles, which is a difference by individual sequences. You see there are kind of a lot of difference in the part of the sequences, which is this. Like this is, for example, is repeating the success, right? The student, like brand of success. People want to see it again and again, like, I don't like this rats. So what we try to do, we try to provide guidance for them, and it turns out that in fact successful students are closer to each other than extreme cases. So apparently being extreme on confirming or non-confirming is not good. So as long as we can identify who the student is he belongs to the group of confirmers or non-confirmers, we actually can give him the right advice. And it turns out that without that, it's hard to give the right advice. Just looking at the student and say, he did it 3 times. All right, should we say go on? Or should we say, no, do once again? It turns out that not only depends on the student current knowledge, but the student part of learning, their personality. So that's so far kind of encouraging result. We repeated several times. This is learning genome, works really like a champ, so I really recommend you. So one last part, again, I will have 25 minutes and questions, is how we work on open corpus adaptive textbook. So we did a lot of adaptive textbooks in the past, when we can guide the student to the right pages, but the trouble is every single page has to be annotated by concepts and prerequisite and outcomes, like here. So this is a page in the textbook. There's a prerequisite concepts, outcome concepts, provided by the teacher, instructor, and domain engineer together, and then we can trace what the knowledge are. Now, actually, the textbooks really provides a very good instrument to get help. If you get stuck on that page, there are two ways. You can use the interface because you see what in fact is the background, what is the outcome. If you like, you can check what is the background knowledge you get and figure out what I might miss, right? Then you can click on the knowledge you miss and you get access to pages which can help you to bring this knowledge gap down. On the other hand, we can ignore that and just use intelligent recommender system approach, push the button, and we'll tell you what to do. This is kind of a work together with you. This is we tell you what to do. We push the button and the system, and the classic recommender system approach generates you the set of pages which should be helpful for you if you get stuck. So this is where we can use this prerequisite outcome data to fuel the recommendation algorithm. This is when we just present them as a part of the interface, and both parts actually works. We have data which showing that. So now how we can get it if we don't have humans who annotate it? Well, that's actually one of our challenges, and there are a bunch of other challenges in our project. But we would like to do this open corpus electronic textbook, but I just want to focus on this, right? So the challenge is how to annotate section with prerequisite outcome pages. It turns out that a lot of work has been focusing on extracting concept from the books. But concept is not enough, and it's mostly done in the field of information retrieval. Well, we need it pedagogically, what this page is really about, what the teacher wants to say on this page. And that means if somebody has troubles and doesn't understand specific concepts, where exactly we need to send that? So this is exactly the pages which provide critical information about some knowledge. This pages has this issue of concepts as a target. So if you miss something here, this page is good in presenting that. So we need to know what is the outcome concept, not as a prerequisite concepts. Well, then of course there is a lot of other changes which still need to get trace student learning, estimate the knowledge get from the learning on these concepts, and figuring out what is the next thing to do. But this is, I think is enough, and we collaborated with Igor, Labutov, who is sitting there, so we're trying to extract the knowledge from the wisdom. And let me give you just at least a glimpse of that, but good enough, it's a KDD poster which is presented right today. Even if you're leaving today, you still have a chance to look at the poster. So the idea here is generative work. Teachers, when they think about writing a textbook, they in fact have the set of concepts in mind. They have some idea what exactly they want to say, and they put that in the structure of the book, right? This mind picture in the human minds being represented afterwards in the structure and the representation of the textbook. So potentially we can reverse engineer that and figuring out what was before that in the teacher's mind, what exactly they wanted to say. And we use two hypotheses which suggested by Igor. So first of all, unit cohesiveness. We assume that in a good textbook, you really want one place where you present specific concept. You don't want to spread it piecewise in multiple places. So we just need to find where it is. Another one, if you really want to tell something in the chapter, frequently you would like to put it in the title, so people can find it easily. So these two ideas, on the top of general ideas of concept extraction from knowledge, might potentially help us. So Igor suggested two models. The first one, how to express that the concept outcome is present only in one place, cohesiveness. And in fact, that's a very challenging issue because just by mining the concept extracted from the pages, you will not be able to get it. It's very frequent that you first start talking about the concepts early, in different concepts, in different contexts, and only somewhere late in the middle, you really present it in details. You can say in the beginning, oh, this book will tell you about relevance feedback and Boolean model of search, and this is it. Keywords are there, presentation is not. Presentation is somewhere in the middle of the book. So here, for example, we talk about conditional gains. Mentioned before, talked about here. And another model which tried to express that concept appearance will likely be expressed in the title is encoded in this model. And well, to make this a long story short, go to the poster, and it looks like what we just did. It's actually worked quite nicely. We get the multiple textbooks from a very nice rich brand new set presented in the open source textbooks. And it looks like we can train the model so that it can actually be used in other different domains. And I have to skip a bunch of other stuff which we're doing in our group, but this is a bit more related to what everyone else is doing. Might not be really that interesting for everyone else, but you can ask me questions about it. And then acknowledgements, our group, and if you didn't get anything from my talk right now, I have to speak very fast. There are still links, you can still do it later. And we have 2 minutes for questions. Thank you very much.